Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at a sort of an illustrative example where we will see that monotone functions enjoy a certain property that right limit and left limit at each point of the domain exists. But before that, let us briefly recall what we did the last time. So what we first defined was the notion of an accumulation point of a subset S of R. So point X in R is said to be an accumulation point of S if every deleted neighborhood of X, meaning a set of this form, or okay, a deleted neighborhood is not just a set of this form, but a set of this form where U is the neighborhood of X. So every set of this form has a point in S. So S kind of doesn't leave X alone, you could say. So that's the notion of an accumulation point. And now suppose we have a function and we have an accumulation point of the domain, and please note that this may not necessarily be in the domain of the function. So okay, I said something incorrect. So suppose you have a function and you have some accumulation point of the domain, and x0 may not be in the domain itself. That is completely fine. Then we defined many things. One of the things we defined was this notation. This means that as you come closer and closer to x0, while of course remaining in the domain of f, the function becomes closer and closer to L. That's what this means, and we gave a precise definition to it. It was just like the epsilon delta, which I do not want to repeat. So when this happens, meaning when there is a real number L such that this happens, we call that the limit exists. Which limit? This limit exists. And if this does not happen, meaning there is no real number for which this equality holds, then we say limit does not exist. In particular, it may so happen that this is equal to infinite, which we define what is meant by this equation, plus infinite or minus infinite, and we say the limit does not exist. But this is not the only case when we say the limit does not exist. So we give an example of this sawtooth like function where this was our x and y axis and the function was something like this. So its amplitude was sort of 1 and minus 1. It took the value plus 1 and minus 1. But as you come closer and closer to the origin, its frequency of vibration kind of increases. So in this case, neither this happens nor that happens. This is a extreme case of the limit not existing as you approach 0. Okay. And then we define the notion of this kind of limit where you're approaching infinite and not a real number. And we defined it, suppose you have S is unbounded, meaning this happens, then if there is a real number such that we can write this equality, and we define what this means in the last time. So if this happens, we say the limit exists. If not, then the limit does not exist, and so on and so on. And then lastly, we gave the definitions of right and left accumulation points and left and right limits of a function. So if your x0 is a right accumulation point of a function f defined on a domain S, then we write this to mean that the right limit of f at x0 is equal to L, and again we gave a definition of it which was very similar to this one, but it was one-sided. Similarly, we have this notation for the left limit, x going to x0 minus f of x, and this may be equal to real number or plus infinite or minus infinite or anything. It could be anything. Similarly for this, it could be plus infinite or minus infinite. And yeah, so there were a bunch of definitions basically the last time. These are the problems, and now let us get on with the material of this lecture. So what we do is we start with a monotone function, and for simplicity I've kept the domain of the function as the entire real numbers. You can easily generalize it to just arbitrary intervals, but anyway, this lecture is more or less like an illustrative example. I was intending to give this as an exercise, but then I thought that this is actually something that I can cover in one lecture so that we understand the notion of the limit better. Alright, so we have a monotone function, so either increasing or decreasing. So the proposition is that then both the left and right limit of f exist at each point of R. So left and right limits exist everywhere. Let us look at an example before we get into the proof. So here is our step function. Sorry. Okay. So here if you take this point, let's say this is your point of the domain, then what is the limit? Let me call it x0. So limit x approaching x0 f of x. Well, this is equal to f of x0. Just think about it, because if you take a deleted neighborhood of x0, the function is actually constant in it, provided you take a small enough neighborhood. And then the function is actually constant. So it's fairly obvious that the limit at this point would be same as fx0, which is equal to 1. This is equal to 1. But what about this point? Here the right limit is 1, but the left limit is 0. So the left and right limit can be different. That's the point. And let me just also draw one more example where well, okay, I'll get to that, but let me start the proof. So without loss of generality, so this means without loss of generality, assume that f is increasing. So if f were decreasing, this a very similar proof goes. So I'm not doing that. So that's why I write without loss of generality. And now let us fix a real number, and we will show that the right limit exists. And similarly, one can prove the left limit, and that half I will leave as an exercise. So we'll just prove the existence of the right limit. And here is the main observation or main idea of the proof is to locate the limit conceptually first and then prove that it is indeed the limit. So here is an example. This is x0, and this is the graph of the function f. Then intuitively the limit from the right of this function should be this guy. It shouldn't be this guy. It is this hollow thing, meaning this value. And we can capture this via this definition. So define L as the infimum of fx as x is strictly greater than x0. And if you just match this definition with this diagram, you will see that yes, this is indeed capturing this point. So this picture is what is informing this definition. But for the proof, you don't need to look at pictures. The proof will be completely rigorous and formal. So it's not like we'll be relying on pictures for making arguments. Okay, so assume on the contrary. So we claim that, we'll show that this limit is actually, the right limit is actually L. And now assume on the contrary. So here is really where the proof kind of starts. That this limit This is not equal to L. Okay, so what does this mean? This means that thus there exists epsilon greater than 0 such that no delta works. So what does this mean, that no delta works? This is informal, but formally, or rather in particular, if you choose delta equals 1 by 100, that does not work, meaning there is a point between x0 and x0 plus 1 by 100, where if you take the value of the function that deviates by at least epsilon from L. That's what it means that 1 by 100 does not work. Similarly, 1 by 101 does not work, 1 by 102 does not work, and so on. Alright, so thus, or rather I would say that is, or in particular, thus there exists epsilon greater than 0 such that, or let me write that is, such that for all natural numbers n, this is an n, there is xn lying in this interval x0 comma x0 plus 1 by n with the property that f of xn minus L is at least epsilon in the absolute value. So this is for all n. Right, I have already written for all n. Okay. So, but note that since xn is greater than x0 and L is the infimum over all x's exceeding x0, in particular, this set already contains fxn in it because xn is greater than x0. So this infimum is, it cannot be greater than fxn, which means L is at most fxn, and hence this absolute value can actually be dropped. So I will drop it without introducing a new line. So this can be dropped basically. Okay. Therefore, fxn is at least L plus epsilon for all n. Okay. Now, since f is an increasing function, this implies that fxn, or rather fx, is greater than equal to L plus epsilon for all n greater than equal to 1 and for all x greater than equal to xn. So here is where we are using the fact that f is increasing one more time. We used it here, but we use it one more time. Okay. But here is the final thing. But note that xn converges to x0. And the reason is very simple, because here is x0, here is x0 plus 1 by n, and xn is somewhere here in between the two things. So therefore xn is less than 1 by n away, or at most 1 by n away from x0. So it is coming closer and closer to x0, and hence it converges to x0. Okay, so if you combine this by the above thing, and let me label this as star, this in combination with star leads to the fact that yields that fx is greater than equal to L plus epsilon for all x greater than x0. And please realize this implication that this plus star actually gives you that. It's not hard at all. Okay, and therefore the infimum of, okay, let me not write this first. So the infimum of this set, sorry, this is at least L plus epsilon, because each of this value by this line is at least L plus epsilon, and hence the infimum is also at least L plus epsilon. But this infimum by definition was L, and this is a contradiction because epsilon is positive. So this is a contradiction. This contradiction proves that this limit is indeed L, and we are done. So simple argument, but not exactly a trivial argument or a straightforward argument, if you will. There's just basically one idea is to come up with this definition. The rest kind of works itself out. But anyway, so as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.